introduction. So, as it says, I'm Sammy King. I'm a senior data engineer at StreamAI, where we use machine learning to help manufacturers understand their products better. And today I'm going to be talking about unsupervised anomaly detection, lessons from the dark arts of the machine learning world. So, to understand anomaly detection, we really need to understand unsupervised learning and why it matters. So, as most people in this room are probably aware, there's been a kind of Cambrian explosion of data in the last decade. So everything from YouTube videos to IoT sensors coming online means there's been this real exponential growth of the amount of data being collected and stored. What some of you might not know, though, is that less than 1% of this data can be considered to have explicit labels. So an explicit label here means some explicit tag linked to that data, which shows that the data shows a category or an outcome that data represents. So for example, if unlabeled data was all of the pictures on the internet, labeled data would just be that subset of pictures which have an explicit tag saying, this is a picture of an apple, or that's a picture of an orange. Why am I talking about unlabeled and labeled data? Why does this matter? Well, the truth is that supervised learning, the dominant form of machine learning today, cannot work with unlabeled data. It can only work with labeled data. Another way of putting that is that unsupervised learning, which doesn't require labeled data, has a potential unlocking analysis for the other 99% of data in the world. As I will show in this talk, though, obviously this comes with quite a lot of complexities and caveats, which make this quite a tricky task. So I think Jan LeCun, the head of AI research at Facebook, maybe puts this best when he said, if intelligence is a cake, then unsupervised learning would be the cake itself, and supervised learning would be the icing on the cake. We know how to make the icing, but we don't yet know how to make the cake. So the thing to really take away here is that the difference between machine learning and traditional rules-based options is that machine learning actually has to learn from the data, right? So in a supervised approach, we see the difference between a model output and the real label. That's why it requires labels to work. And we can use that to automatically tune our model. But the question is, in unsupervised learning, we don't have access to these labels, right? So how do we learn from the data in this context? And that's why I called this talk Lessons from the Dark Arts. It's really unclear how to do this, and in many ways, unsupervised learning is kind of the dark side of machine learning, where many of the normal rules really don't apply. So, lesson one. Unsupervised learning holds a lot of promise for unlocking insights in unlabeled data, but it's unclear how we really learn from that data. So, how can we learn from data in an unsupervised world, and particularly in an anomaly detection context? Well, the good news is that there's a lot of different options for getting feedback from data in an anomaly detection context. The bad news is they all kind of suck. So basically, one thing we could do is we could get labels for the data. This is good. It brings us back to the nice, safe, supervised world. But it's obviously hard and expensive to get labels, and this really doesn't scale, and it kind of undermines the whole benefit of unsupervised learning that we just talked about. Another thing that we could do is we could eyeball the data, we could plot our raw data and our model scores, and we could see if our model makes sense. And that's kind of a good way of ad hoc checking if these anomaly detection models are working. The bad thing here is it's obviously not scalable at all. It doesn't offer us any objective metrics to tune our model, and it also gives us like no automatic way to do this. So moving on to some kind of more exotic options, we could try something called synthetic injections, which is where we take our data, we inject synthetic anomalies into it, and we can then see how well our model can actually detect these. This is kind of cool because it's scalable, it offers us some objective metrics, and it even has a nice sort of feature that we can design different types of synthetic anomalies to see how well our model generalizes. The problem here is it's not at all clear that actually synthetic injections relate to the real world, so we may end up training a model which is really, really good at detecting synthetic injections, and as soon as we put it in production, it just falls apart. And so a final thing that we could try is something called proxy cost functions, which I'm going to go on to explain in a bit more detail in a moment. But it's basically something else that we can measure in the data that we can use instead to try and tune our model. This is cool because it's scalable and it offers us some kind of objective way to tune our model, which is cool. But it comes with many assumptions, which we'll explore in a minute, and it can lead to some kind of perverse optimization outcomes. So, Lesson 2, there's lots of bad ways for getting feedback in an unsupervised world. So use them all. Any metrics you have to validate your model need to be carefully collected and analyzed. So in the previous slide, I talked a bit about proxy cost functions, especially in an anomaly detection context. Probably some of you are now wondering what the hell is a proxy cost function anyway. So to understand the proxy cost function, we first need to understand a little bit about what a cost function is in the supervised model. For some supervised model, in this case a basic linear regression, we have some model that maps an input to our model's output via some data parameters that the model itself can update. We then define a cost function which maps these data parameters to some outcome that we care about, in this case reducing the mean square error between our model outcome and the label. And then we define some update strategy to iterate over this process until we find the theta parameters that give us the best possible cost function. And this way we can automatically tune our model. This is how supervised learning works. Unsupervised learning, obviously this doesn't directly apply because we obviously don't have any labels. But we can use a proxy cost function here, so that's something else that we can measure in the data, which we could correlate to the actual goal that we're trying to achieve, and use that in a similar process to try and optimize our model automatically. So one example of a proxy cost function in anomaly detection that we could try is to try and maximize the distance between a low and high anomaly scores. So the logic here is that we have some data with some normal pieces and some anomalous pieces, and we run our anomaly detection model, and we should get some anomaly scores for our pieces, hopefully with two distributions, one that represents normal guys and one that represents anomalies. And then we can measure, don't worry about the maths, but we can measure the distance between, for example, the peak of these two distributions, and define a cost function which tries to update our model to pull these apart as much as possible. So the idea being that we end up with a model which is trained to discriminate between normal guys and anomalies, which sounds great. This obviously comes with the assumption that there are two distributions in the anomaly scores that we actually that we can actually pull apart. But it seems like a good idea, so let's give it a try. The problem, as probably some of you in this room have already realized, there's a lot of ways that this can go terribly, terribly wrong. On the left here, we see another set of anomaly scores, this time with kind of two bumps on the right, one representing a more obvious type of anomaly with a higher score, and one representing a more nuanced anomaly with a lower score. And on the right here, we have three different outcomes, all of which kind of honor the proxy cost function that we just defined, but with slightly different random initializations. In the top, we see this goes great. Both of the types of anomalies are pushed to the right, and we are clearly separated from the normal guys, which is great. However, in the second case, we see that the more subtle type of anomaly is actually subsumed to the left and pulled into the normal function. So what we've done here is we've created a model which is really good at detecting very obvious anomalies and terrible at everything else, so this doesn't seem like a great outcome. And potentially even more extremely, at the bottom case, we have one high anomaly scoring piece, and this is enough to push all the other type of anomalies into the normal left side, leaving us with kind of a terrible model that's not at all optimized for what we actually care about. So this is kind of a bad example of a proxy cost function. And more than that, I said a minute ago that this proxy cost function has an assumption that there are two different distributions, one for normal and one for our anomaly scores. So what happens if we try and put this through a clean channel, that is something that has no real anomalies? Well, to honor our proxy cost function, we still need to have two distributions, so it will arbitrarily choose a higher scoring piece and push and use that as the modal piece for the anomaly score. So we again honor the cost function, but we end up with a totally crap model. So, so lesson 3, proxy cost functions can be a good way to tune models in an unsupervised world and for anomaly detection, but PCFs are not the outcome itself. This is the important thing. So we really need to understand what they mean, what assumptions they hold, when to use them and when not to use them. So in the last part of this talk, I want to show how PCFs actually can be used fruitfully for anomaly detection, but to do that I first want to talk a little bit about the sort of special way that we look at time series data at StreamAI. So can we look at time series data anomaly detection differently? Well, you guessed it, we can. Especially for periodic time series data, so that's machine sensors often show this kind of distribution, but something with a periodic signal. We can take our sequential time series data and we can chop it up into the recurring cycles and kind of put them on top of each other. So to view the problem spatially, where each cycle is the fundamental unit as compared to each other. So a spatial approach has some kind of cool features, at least visually. It's quite easy to see a lot of cyclical data at once if you plot everything on top of each other. It also makes it pretty easy to see anomalies because you can see that they diverge from the normal behavior. And kind of even more interestingly, we can see that we can even see different patterns of normal. So here you see the blue and the green, which are both kind of normal behaviors, but different ones. We can see this all in one place. As I'll speak about in a moment, it also has some nice features for actually designing better anomaly detection models, but it's worth saying here that this does obviously come with some drawbacks. So a spatial approach obviously disregards to some extent the auto-correlated time series nature of the data. It works best on strongly periodic signals like machine sensors, and for some sensor types like audio sensors, you need to do quite a lot of pre-processing to show this kind of cyclical pattern. Right. So, lesson 4. Periodic time series data can often be translated into a spatial problem, comparing data on a per cycle basis, though it works best for strongly periodic data with clear cycles. So, yes, finally, as I said, how can we apply PCS and a spatial approach to machine learning for time series anomaly detection? Now, there's quite a lot of unsupervised algorithms already out there in the wild for doing anomaly detection on time series data. And today I'm going to look at 3 of them and show how both the spatial approach and proxy cost functions can really be used to sort of improve these models. Okay. So the first one here is dynamic distance density clustering. Basically, how does this work? We take our data, we chop it up into cycles, and then we measure the distance between each cycle and every other cycle to create a kind of distance matrix. Now, there's lots of different ways we could measure this distance, but in this case we use a kind of non-Euclidean distance, something called dynamic time warping, and we end up with this distance matrix. And then finally, we can cluster this distance matrix to end up with groups of cycles who kind of represent normal patterns of behavior, and guys who don't fit into this at all, which represent anomalies. So the first thing to mention here is obviously this harnesses this spatial approach to make the time series problem a lot simpler. Now we just need to look at the distance between each cycle and every other cycle in a spatial way, rather than having to deal with arbitrary bits of time series data. The other really interesting thing here is we can use the proportion of clustered cycles. So that's the number of cycles that end up in some cluster, say for example at least 90%, as a, you guessed it, proxy cost function to help automatically tune the clustering stage of our model. This obviously assumes that most cycles are normal, which seems like a fairly reasonable assumption for in the anomaly detection context. But the cool thing to note here is that we use the proportion of clustered cycles as a proxy cost function just to tune the clustering part of the model. And that means that we kind of constrain some of the potentially perverse outcomes by only updating those data parameters to do with clustering. So this is kind of a good example of how you can actually use PCS to improve anomaly detection models. Next, we have auto-encoders. So how does an auto-encoder work? Basically, we take some data as an input, we push it through a neural network architecture with some constrained layer in the middle, some constrained hidden layer, and then we reconstruct it on the other side as an output. We can then measure the difference, the reconstruction error between that output layer and this input as a kind of way to express how well the model is able to summarize our data, how well it's able to push it through a small space and enlarge it again. Again, we can use a spatial approach here to simplify this problem. So autocorrelators are notoriously difficult to deal with time series data because you have arbitrary lengths of time series. So we can simplify it input-output space by saying we're going to give you just a cycle as the input, and you're going to give me back just a cycle as the output. So we can use a spatial approach to simplify this problem. And one thing you might notice about this reconstruction error is it also is a natural proxy cost function. So the reconstruction error represents how well the model is able to reconstruct a normal cycle in this case, which the idea being that it's very closely related to the task that we actually want to achieve, which is how normal the cycle is or how anomalous it is. So this is a very good case of where a spatial approach can simplify the problem, and a proxy cost function can be used to you can use it without labels to help automatically tune our model. And finally, we have GANs, which are generative adversarial networks. So how do these work? Basically, we have one model called the generator, who generates synthetic pieces of data, and then passes this to another model, the discriminator, who has to tell whether the data comes from the made-up fake data or from the real data. And then we can use the classification performance of the discriminator itself to train both models. So we end up with a discriminator which is good at detecting normal and synthetic data, and a generator which is able to generate very fake but subtly fake pieces of data. So again, we can use a spatial approach to simplify this problem. Now, instead of generating arbitrary pieces of time series data, we can tell the generator just to generate a cycle, which obviously massively reduces the complexity of the space. And simultaneously, the discriminator only needs to tell the difference between one cycle, a fake and a real cycle. And again, the classification performance of the discriminator is again a really clear proxy cost function. So the classification performance of the discriminator tells us how likely it is to be a normal guy, or in some ways synthetic or abnormal. So again, we have a proxy cost function which directly relates to the goal we care about, but without using any labels. So lesson 5, both PCS and the spatial approach can be a good way to build some really powerful anomaly detection models, but we need to design them carefully in order to benefit from these techniques. So, conclusions. What have we learned today? We've learned unsupervised learning holds a lot of promise for unlocking analysis in unlabeled data. That there's lots of bad options for getting feedback from unsupervised anomaly detection, so we need to use them all. The PCS are a good way to tune models, but we need to be very careful about how we actually use them. The periodic time series data can be translated into spatial problems with some nice features to help simplify our problem space. And both PCS and the spatial approach can be a good way to build some really powerful anomaly detection models in an unsupervised setting. So, which leads me to my final lesson. Unsupervised anomaly detection is really tough. You don't have any of the nice safety nets that you have in supervised learning, but it forces us to think very carefully about the approach we take to machine learning, and to use all the tools to solve these problems, solve these very difficult problems, which is really what's so fun about data science in the first place. So, thank you. My name is Simon King. Feel free to come and talk to me afterwards if you have any questions.